DGAZE, driver gaze mapping on road. Can we determine where a driver is looking? Is he paying attention to the pedestrian crossing the road or not? In this work, we are trying to predict the gaze of the driver by mapping it to objects on the road. Driver gaze information can be used to measure the attention and fatigue of the driver and to find objects of importance on the road. Currently, driver gaze datasets are collected using eye tracking hardware, which are expensive and cumbersome and thus unsuitable for use during testing. In this work, we introduce DGAZE, a driver gaze dataset, to map the driver's gaze to points on the road using low-cost mobile phones. It does not require expensive or proprietary equipment during deployment. Our dataset is collected in a lab setting mimicking the real driving conditions. A driver sits in front of a car backdrop and looks at specific objects on a road video projected in front of them. A mobile phone is mounted on a tripod stand and used to collect both driver and road videos simultaneously. We collect 1 lakh image pairs and extract them from 2,000 road and corresponding driver videos. We have 103 clips of the road view, each one annotated with an object from one of the 7 object classes. Here is the distribution of the object and point annotation on the road video. The object annotations are shown in red and the point annotations in blue. The driver video is of 20 drivers who are asked to look at the projected road videos. Here are some examples. We collect videos of both male and female drivers with and without spectacles and having a wide range of heights. Here we see the spatial distribution of the facial features of a driver as a heat map. The left eye is shown in blue, the right eye in red, and the mouth in green. We also introduce I-DGAZE architecture for predicting driver gaze on the road. I-DGAZE is a late fusion convolutional neural network with 2 branches. We input an eye image to one branch and the face area, head pose, and face location as input to the second branch of the network. The output obtained is the predicted eye gaze on the road. The green and red points represent the ground truth and predicted gaze respectively. We then use 900 images of drivers looking at 9 calibration points to fine-tune the I-DGAZE network for driver-specific gaze prediction. Here we present the I-DGAZE results, which are predicted frame by frame. Sequence 1 shows the driver looking on a motorbike coming from one side, but the prediction flickers a lot between the motorbike and nearby objects. After calibration, the prediction stabilizes on the motorbike. Sequence 2 shows the driver looking at a car crossing in front of him. Even though the predicted point is on the correct object, there is a high pixel error. After calibration, the pixel error reduces. Sequence 3 shows the driver looking at a traffic signal. Since the object is small, a small pixel error is critical. After calibration, the error reduces and the prediction falls on the correct object. We observe an error of 94.5 pixels on the DGAZE dataset without calibration and 45 pixels with calibration. We compared our method with 3 standard gaze prediction methods trained on the DGAZE dataset. Our method outperforms other methods in terms of pixel error. Here we see the results of ablation method experiments on our method. The first 2 rows use only the eye images, which are not adequate. In the 4th row, which is our method, we add head pose, face landmarks, and facial area, which gives the best results. In the 5th row, we add the right eye image also, which did not improve the performance. Our dataset, code, and models are available online. Thank you.